Welcome to the BioniChaos live stream. I'm thrilled to have you all here today as we explore some of the most exciting projects and applications on the BioniChaos website. For those of you who are new, BioniChaos is all about democratizing biomedical data processing, creating interactive tools that help us visualize and understand complex biomedical signals like EEG and ECG, all using open source software and hardware. Today, I want to dive deep into some of the latest applications we've been developing. One of the highlights is Cardio Rock, a game where you can test your skills in identifying abnormal ECG waveforms. It's not just fun, it's also a powerful educational tool. We use dynamic rock curves to provide real-time feedback on your performance, helping you learn and improve as you play. Whether you're a student, a researcher, or just curious about cardiac science, this game is a great way to engage with the data and challenge yourself. I'm also really excited to talk about Rhythm Scan, our EEG seizure detection tool. This application allows you to visualize EEG spectrograms and analyze machine learning models to understand how they detect seizures. We'll walk through the interface, explore key metrics like accuracy and loss, and even dive into some of the confusion matrices that show us how well these models are performing. This is especially useful for those of you interested in the intersection of AI and healthcare. Now, I've noticed that a few pages, like ECOG and Color Shift, are returning a status code 500. It seems we've hit some bumps on the road, but no worries. This is part of the development process. I'm going to walk you through what might be causing these errors and how I plan to troubleshoot them. Maybe it's a server-side issue, maybe a broken link. Whatever it is, we'll get to the bottom of it together. If you have any questions about these applications or want to see a live demo of any specific tool, just drop a message in the chat. We'll try to cover as much as we can, and I'd love to hear your thoughts and feedback. Also, for those of you who want to contribute or support the project, remember that BioniChaos is a work in progress. You can find updates on the website, and I'm always open to feedback through our contact page or even here in the live chat. If you enjoy what you see and want to support further development, consider checking out our Patreon. Every bit of support helps keep these tools free and open for everyone. So grab your favorite beverage, settle in, and let's dive into the world of biomedical data. What would you like to explore first? All right, let's keep this momentum going. I see a lot of interest in the chat around our EEG applications, so let's dive deeper into some of the unique tools we have on the BioniChaos site for analyzing brain data. First up, let's talk about Seizure Fuzz. This tool is designed to make EEG data analysis more interactive and intuitive. With Seizure Fuzz, you can select specific EEG IDs, patient IDs, electrode locations, and even specific timeframes to visualize different aspects of the data. It's great for both newcomers and seasoned researchers because it allows you to really hone in on the details that matter, like spectrograms or seizure event markers. I'll bring it up on the screen now so we can walk through a live demo. As you can see, the interface allows you to choose from various drop-down menus. You can filter the data by different parameters and instantly see the results in multiple dynamic charts. These charts can be expanded, zoomed, or even downloaded for further analysis. This flexibility makes it easier to identify patterns, understand EEG signal variations, and gain new insights into neural activities. Now, let's shift gears and look at something really cool, EEG to music. This tool is one of my personal favorites because it brings a creative twist to EEG analysis. Instead of just visualizing EEG signals as traditional waveforms or power spectra, this application translates EEG data into music. Yes, you heard that right. It's like listening to your brainwaves. We use various algorithms to map different EEG frequencies to musical known notes, creating a unique auditory experience. Let me play a sample for you. Pretty fascinating, right? This isn't just a novelty. It's a powerful way to engage new audiences with EEG data, making it accessible and interesting even to those without a deep technical background. I see some questions in the chat about how this is done. Essentially, we take the amplitude and frequency components of the EEG data and map them to corresponding musical scales or instrument sounds. This approach helps us perceive patterns in the data that might not be immediately obvious through visual analysis alone. Now let's get into something a bit more technical, the NeuroGPT project. This is where we blend advanced neural network architectures, like generative pre-trained transformers, with EEG data. We're pushing the boundaries of what's possible by using AI models to analyze brain data in ways that were previously unimaginable. We're talking about real-time analysis, pattern recognition, and even prediction of neural states. I'll be sharing some insights into how we train these models, the datasets we use, and the challenges we face, like handling noisy data or balancing model complexity with computational efficiency. I'm also seeing a few questions about the errors on the site, like the status code 500 for pages such as ECOG and color shift. For those just joining, this means that the server encountered an internal error when trying to load these pages. It could be due to a variety of reasons, maybe a problem with the database connection, a bug in the code, or even a misconfiguration in the server setup. I'll walk you through my process for diagnosing these issues. I usually start by checking the server logs to pinpoint the exact problem, then look at any recent changes to the code or server settings that might have triggered the error. We'll tackle this live, so if you have specific questions or want to share your troubleshooting tips, let me know. For everyone just tuning in, feel free to ask questions or suggest a tool you want to see next. We can look at anything from our gait analysis application, which uses heat maps to visualize foot pressure during walking, to our CRISPR simulation lab, where you can experiment with gene editing. All right, I'm seeing some interest in the chat about the gait analysis application. Let's take a closer look at that next. This tool is all about understanding how we walk, and it uses dynamic visualizations to show the pressure distribution on the feet during different gait cycles. It's super useful for understanding normal versus abnormal walking patterns, which has applications ranging from sports science to rehabilitation medicine. Let's load it up, and I'll show you how the interactive elements work. You can adjust the parameters like stride length, speed, or pressure thresholds, and instantly see how these changes affect the gait pattern. It's a powerful demonstration of how small changes in biomechanics can have a big impact. I'm loving the energy in the chat today. Keep those questions and comments coming. What do you all want to explore next? Absolutely. If I had to pick the most interesting tool on BioniChaos, I'd say it's the Vision Impairment Simulator, Vision Sim. Why? Because it brings a unique perspective to how we perceive the world and leverages technology in such a compelling way to build empathy and understanding. Vision Sim allows users to experience firsthand what it's like to live with various visual impairments. It's a simple idea with profound implications, especially for designers, developers, and even educators who want to create more inclusive environments. What makes Vision Sim particularly fascinating to me is the way it uses real-time adjustments to simulate different conditions like myopia, cataracts, or glaucoma. You can tweak parameters like blur levels, contrast, and color saturation, and immediately see how these changes affect your ability to read text, recognize faces, or even navigate a scene. It turns abstract medical conditions into tangible experiences, making it easier to understand the daily challenges faced by people with visual impairments. I also love that this tool goes beyond just education and awareness. It can be a game changer for accessibility design. Developers and designers can use it to test how their websites, apps, or products appear to users with different types of vision issues, ensuring that their work is accessible to as many people as possible. And on top of all that, it's an interactive experience that draws you in immediately. It doesn't require any prior knowledge to use and provides an instant, visceral understanding of the topic. That blend of accessibility, education, and empathy is what makes Vision Sim stand out for me. If you haven't tried it yet, I'd encourage you to check it out. It's a great way to see the power of web based tools in transforming complex medical and social concepts into something everyone can understand and engage with. Sure thing. Let's keep it casual and fun, like we're all just hanging out here together. All right. If I had to pick one tool on BioniChaos that I think really needs a bit more love and development, it's got to be Seizure Fuzz. Now, don't get me wrong, this tool has a ton of potential. I mean, who wouldn't want a tool that lets you dig deep into EEG data and visualize all those brainwave patterns like some kind of data wizard? But I think there's a lot more we can do to make it really shine and maybe even give it some personality. Right now, it feels a bit like that awkward friend at a party who has so much to say but just needs a bit of a confidence boost to get going. Think about it. EEG data is like this big, mysterious ocean of squiggly lines and signals. And Seizure Fu is your boat. But at the moment, It's a bit like a rowboat. What we really need is to turn it into a flashy yacht with all the bells and whistles, where you can zoom in on every single wave and really understand what's happening beneath the surface. I'd love to see more interactive features where you can grab the data with your virtual hands, stretch it out, and zoom in on those funky parts that look like they might be important, like when you're trying to find that one curly fry in a pile of regular fries. And let's talk about the analysis side of things. Right now, it's mostly just showing you what's there. But imagine if it had a bit of AI magics sprinkled on top. Maybe it could start spotting patterns or even predict when something interesting is about to happen, like a sports commentator saying, "Ooh, watch this part right here." We could add some fun like, "Danger, Will Robinson, seizure alert incoming." Or maybe even a little animated brain that does a dance when it spots something unusual. That would definitely keep things interesting, right? But also, I think we need to make it a bit more user friendly. Right now, it feels like trying to read the menu in a dimly lit restaurant. You kind of know what you want, but you're squinting and feeling a bit lost. We could make the interface clearer, add some helpful hints, maybe even a quirky virtual assistant who pops up and says, "Hey, I see you're struggling with that spectrogram. Want some help?" Something that makes it feel less like you're working and more like you're on an adventure, discovering new things about the brain with a trusty guide by your side. And here's a crazy idea. What if we turned seizure fuzz into a bit of a social thing? Imagine a feature where you could share your findings, maybe even challenge a friend to analyze the same data and see who finds something cool first, like a treasure hunt for nerds. Or maybe create a leaderboard for the best data detectives out there. It could be like Pokemon for EEG. Gotta catch those seizures. So, yeah, Seizure Fuzz has a lot going for it, but it's like a diamond in the rough. With a bit more polish, a splash of fun, and some extra features to make it pop, it could go from being that tool you occasionally use to the one you can't stop playing with. And honestly, that's what I'd love to see happen. Turning these tools into something people are excited to use every day. So, what do you guys think? Ready to turn Seizure Fuzz into the life of the party? Hey everyone, welcome to the stream. I see you're diving into some serious server side stuff today, so let's make it a bit more fun and interesting. We've got a script here that does a great job of checking the health of a website, looking for broken links, missing content, or any pesky errors that might pop up and spoil the user experience. So, what this script does is it takes a look at all the pages on your website and makes sure everything is in order. It fetches the HTML of each page and checks if the page loads correctly. If it doesn't find any content, or if it sees some error messages like 404 not found or 500 server error, it makes a note of that and saves it to a log file. It's like having your own little detective going through your website, looking for clues that something might be wrong. But that's just half the fun. The script also goes a step further and creates a sitemap, a kind of map or directory of your website that helps search engines like Google crawl your site better. It's sort of like writing a cheat sheet for Google to help it understand what's on your website, which pages are important, and how often they change. This can be great for SEO, making your site more visible to people searching for relevant content. It even goes the extra mile by fetching all the links from the landing page and comparing them to the actual pages on the site, checking if any are missing or broken. Now, the real challenge we're tackling next is making sure that your web server, the Apache server in this case, stays healthy and happy. Imagine this script as a companion that sits alongside the current one, but instead of checking the website content, it keeps an eye on the server itself. We want a script that monitors the server logs for any signs of trouble. Think of it like an ever-vigilant guard dog, sniffing out any error messages in the server logs and barking, metaphorically, of course, when something goes wrong. It would be monitoring the server for signs like memory leaks, crashes, or unauthorized access attempts. If it spots anything that looks dangerous, it would instantly let you know, perhaps by sending an alert directly to your email or messaging platform. This kind of monitoring is crucial because while your website might look fine on the surface, the server could be dealing with hidden issues that could eventually cause downtime or performance problems. What's more, we could set it up so that it takes action when certain errors are detected. For example, if there's a critical issue, like a memory leak or a major crash, the script could automatically restart the server or specific services to prevent a complete meltdown. It's like having a safety net for your server, ensuring that it can recover from minor hiccups without human intervention, while alerting you to more significant problems that need a hands on fix. And there you have it. We're building a dynamic duo of scripts, one to keep the website itself in check, and another to ensure the server is running smoothly. Together, they'll make sure your site is always ready for visitors and your server remains in tip top shape. Stay tuned as we dive deeper into building this next part of our project, and feel free to ask questions or share your thoughts. We're in this together, after all, so let's make it fun and insightful. Hey everyone, if we're thinking about which tool to focus on next, I'd lean towards Seizure Fuzz. It's already doing some cool stuff with EEG data, but before diving into more development, I'd want to know a few things. How easy is it for you to use right now? Are there any parts that feel confusing or slow? Also, what features do you think are missing that could make it more useful or fun to work with? And for those of you who use it often, how do you see it fitting into your daily work or research? Let me know your thoughts in the chat. Your feedback is what makes these tools better. All right, folks. Looks like we're having a little hiccup with the Seizure Foods tool, and I've got the page pulled up here to show you what's going on. As you can see, we've got a bunch of errors popping up on the right side of the screen, and it's not looking pretty. These little red messages are like the annoying alarm bells in a spaceship movie, blaring, warning, warning, something's gone wrong. So, what are these errors actually telling us? They're all saying 404, which is basically internet speak for, hey, I tried to find this thing, but it's not here. Imagine you're looking for a specific book in a library, but when you get to the shelf, the book is missing. Or worse, the whole shelf is gone. That's what's happening with the data that Seizure Fuzz is trying to fetch. It's looking for specific resources, like EEG data or spectrogram files, and the server is just shrugging back at us, saying, nope, couldn't find it. Now, the reasons for this could be a few things. Maybe the file names have changed, or perhaps they were moved to a different location and the tool hasn't been updated to know where to look. Or, even juicier, there could be a typo in the code, like sending it to the wrong address, kind of like trying to deliver pizza to a house that doesn't exist. The poor code is out there wandering with no pizza party in sight. And look, see that little message at the bottom about third-party cookies? That's a heads up from our browser letting us know that in the future, cookies, not the chocolate chip kind, unfortunately, but the ones websites use to remember things, might be blocked. This isn't causing our current problem, but it's a reminder that we've got some things to keep in mind for future updates. For now, what we need to do is roll up our sleeves and check out where exactly these requests are trying to go and why they're hitting a wall. But that's for a bit later. First, I want to hear from you guys. What do you think could be going on here? Have you run into this on your own projects? And if so, what's worked to fix it? Drop your thoughts in the chat. Great question. From what we see in the image, these errors are being displayed in the browser's developer console, and they are related to HTTP requests made by your web application that resulted in 404 not found responses. This type of error occurs when the client, in this case, the web browser, tries to fetch a resource from the server, such as a specific file or data endpoint, but the server cannot find the resource at the requested URL. Understanding the errors in the image. The console messages shown in the image indicate multiple 404 errors with messages like, failed to load resource. The server responded with a status of 404. Error. Sure. Let's go through each of these log files and explain what they contain and their purpose in your Apache server's logging system. 1. Access.log. This is the main access log for your Apache server. It records every request made to your server, such as when someone visits a page, downloads a file, or requests any other resource. The log includes information like the client's IP address, the request method, get, post, etc., the requested URL, the HTTP response status code, like 200 for success or 404 for not found, the time of the request, and the user agent, browser or client making the request. This file helps you understand which resources are being accessed and how often, as well as to identify any unauthorized or suspicious access attempts. 2. Error.log. This is the main error log for your Apache server. It captures all error messages and diagnostic information generated by the server. This includes errors like missing files, 404 errors, server misconfigurations, script errors, permission issues, and more severe problems like server crashes or memory allocation errors. It's crucial for troubleshooting and fixing problems that occur on the server. 3. Other vhosts access.log. This log file records access requests for virtual hosts other than the default host. Apache can be configured to serve multiple websites, virtual hosts from the same server. This file would contain access logs for these additional virtual hosts. It works similarly to the main access.log, but is specific to those non-default sites hosted on the server. 4. Access.log.1, error.log.1, other vhosts access.log.1. These are rotated log files from previous periods, e.g. yesterday or earlier. Apache uses log rotation to manage the size of log files and keep them from growing indefinitely. The .1 files are typically the most recent archived logs, the previous cycle, providing historical access and error information before the current active logs. 5. Access.log.gz, error.log.2.gz, other vhosts access.log.2.gz. These are older rotated log files, compressed with gzip to save disk space. Apache compresses older logs to keep them for longer periods without using too much storage. The .2 indicates these logs are from an earlier time period, with the .gz extension showing they are compressed. The numbers increase, e.g. bot3, bot4, as the logs get older. Why are these logs important? Access.log files help you monitor and analyze traffic patterns, understand user behavior, and detect potential security threats. Error.log files are essential for diagnosing server-side issues, fixing broken resources, and ensuring your website functions correctly. Other vhosts acts.log is particularly important if you are managing multiple websites on the same server and need to monitor the traffic separately for each. Rotated logs, .1, .2.gz, etc., provide historical data that can be crucial for understanding long-term trends, performing audits, or investigating issues that occurred in the past. Together, these logs provide a comprehensive view of what's happening on your server, both in real time and historically, enabling you to maintain and secure your web applications effectively. Great question. So, should we stash all those Parquet files into a static folder or even a CDN? Well, not exactly. See, .parquet files are like the secret sauce of data. They're not just static content like images or CSS that you toss on a CDN for fast delivery. They're more like the juicy, dynamic ingredients your app needs to slice, dice, and serve fresh every time someone loads up Pfus. We need them to be close to the action, ready to deliver the goods when the data is queried. Putting them in a static folder or on a CDN is like sending your brain to fetch a burger from another city every time you're hungry. Sounds fun, but not exactly efficient. So let's keep those .parquet files where they can be accessed quickly by the server and save our static folder for the lighter stuff.
Okay, so I'm keeping the structure of this seizure fuzz application as is. We do need to sort all the other code so it can access these data files correctly. So we eliminate the errors that we currently have. So can you help me with that? I'll share the code next.
Absolutely. Keeping the current structure makes sense if it helps with quick data access. I'm here to help you get the code sorted so that Seizure Foods can find and load those .parquet files correctly. And we can wave goodbye to all those annoying errors popping up. Go ahead and share the code you've got, and let's dive in to see where the fixes are needed. We'll make sure the application knows exactly where to look for those files so that everything runs smoothly.
Can you, without generating any new code, just go into the details of what's currently going on? Keeping in mind the errors that we are getting at the moment.
All right, let's dive into what's currently happening with Seizure Foods based on the code you've shared and the errors we're seeing on the console. The main problem seems to be that some data isn't loading correctly. resulting in those dreaded 404 errors. Here's what's going on. The application is trying to fetch data from specific .parquet files and resources, but it's getting the 404 not found error, which means that the server can't find the files or resources it's being asked for. Essentially, the app is saying, "Hey, where's my data?" And the server is just shrugging its shoulders. This is happening for both EEG data files and spectrograms. Now, looking at your Flask code, it seems like you're fetching these resources based on parameters like EEG ID, electrode, spectrogram ID, and side. The requests are constructed dynamically, and they're supposed to find the correct .parquet files in directories like train or EEGs and train spectrograms. But if these files are missing, moved, or the file names don't match what the app expects, you get a 404 error. In particular, the 404 errors in the console, like those related to fetch speed 6465110838 side RL1, suggest that the app is trying to access spectrogram data files that don't exist at the expected locations or with the expected names. It could be a typo in the file names, incorrect paths, or maybe the files weren't uploaded correctly to the server. There's also a bit of a data mismatch issue. The JavaScript is dynamically populating drop-down menus with EEG IDs, sub-IDs, and other parameters. But it's possible that these values don't always correspond to actual files on the server. For example, if a user selects a particular EEG ID, the app may try to fetch data for an electrode that doesn't exist in the corresponding .parquet file, leading to a 404 error when it can't find the data. Additionally, the code seems to rely on parsing certain columns from the .parquet files, like time and frequency data for spectrograms. If these columns are missing or named differently than expected, the app won't be able to construct the data properly for display, leading to more errors. Lastly, the 404 errors could also be due to server-side issues. For example, if there are permission problems with the files, or if the file paths are being incorrectly constructed on the server, the app won't be able to access the resources even if they're there. So, to sum it up, the current situation seems to be a mix of missing or incorrectly named .parquet files, mismatches between drop-down menu selections and available data files, potential server-side issues with how file paths are handled. We'll need to check that all the file paths and names are correct and that the data actually exists where the app expects it. Also, confirming that the code handling these requests on both the front end and back end is correctly set up will be key to fixing these issues.
Okay, so I actually moved the data folder into the static folder. We need to update all the parts of the script which actually trying to fetch the data so they do not return an error. Can you do this for me with this updated file and folder structure above? comment that out for a sec. But the GID is not being called properly. It's not defined. Yeah, that response is not great. Okay, can we go step by step and check the entire Python script first for folders, making sure that it works with the current file and folder structure. Can we go over this HTML and make sure it's working with the JavaScript and the Python backend? Yeah, we're using the wrong chat. So you're doing the logging later on. Yeah, no wonder I get confused. We were using the wrong chat. I'm just trying to see how far we went. Yeah, we had the updated structure and all. Okay, I'll close that one for a sec. Okay, let's just start a new one. Okay, let's start fresh. So we have this seizure fuzz EEG data viewer application. Currently having a few errors with it. We have the current structure. We don't worry about the info. Well, not for now. We have the backend. This is what's fetching the data from the server. Okay, so we have the file and folder structure as indicated above. We have our backend, the Flask Python script that essentially meant to fetch all the data. And we have the JavaScript. If you can briefly explain what's going on, just make sure that it engaging for viewers. Just pretend you are live streaming at the moment, and we will be doing further development later on, so don't provide any code in your response. We just wanna see why we are getting certain fetch data errors, as indicated in the image attached. So can you just confirm going over the code, and the image. Continuous sentences, full paragraphs will be great. If you feel like being funny, go for it.
All right, let's dive into what's happening here with our EEG Data Viewer web application. So what we have here is a Flask-based web application designed to let users explore EEG data in all its intricate glory. Think of it as a friendly neighborhood tool for those curious minds eager to understand brain activity. The app allows users to select specific EEG IDs, sub-IDs, and electrodes and visualize their associated data in various ways, from time series plots to spectrograms, all in the pursuit of deciphering those neural signals. Now, let's talk about the hiccup we're seeing in the console on the right side of the image, those 404 not found errors. A 404 means the application is trying to fetch data from certain endpoints, but it can't find the resources it's looking for. Essentially, our app is knocking on the door of /fetch spectrogram, but nobody's home, and that's why we get the not found message. This could be happening for a few reasons. Maybe the endpoint URL is incorrect, or maybe the server-side function isn't properly set up to handle the request. Our Flask app has several endpoints defined, like /get EEG IDs, /fetch EEG data, and of course /fetch spectrogram. Each of these is designed to handle specific types of requests. For instance, fetching EEG IDs, fetching data for a given electrode, or pulling spectrogram data to visualize frequency changes over time. The JavaScript on the front end is trying to interact with these endpoints to populate drop-down menus, update charts, and display spectrograms. However, when the browser tries to call the /fetch spectrogram endpoint, it's hitting a snag. The reason could be a typo in the URL, or maybe even an issue with how the Flask route is set up. Now, on the Python side of things, our Flask app is managing all these interactions. It's reading from CSV files and Parquet files to provide the necessary data. We have functions like get EEG IDs that reads a CSV file to get unique EEG IDs and sends them to the client side. Then we have functions to get patient IDs, electrodes, labels, and even spectrogram data. But if any of these data fetching operations fail, the app is programmed to log errors or return a 404, as we see happening now. Meanwhile, on the JavaScript side, we have a bunch of functions that try to fetch this data and update the UI accordingly. When the user changes a dropdown or selects a new EEG ID, these functions spring into action, making asynchronous fetch requests to our Flask endpoints to get the data they need. For example, if you pick a different electrode, JavaScript will call the backend to fetch the relevant data, update the plots, and keep things dynamic and interactive. But right now, since the /fetch spectrogram endpoint is not working correctly, those functions can't do their job, and hence the console is flooded with red error messages. So the first thing we need to do is double check our Flask routes and make sure they are correctly defined and accessible. We also need to ensure the paths we're using in our JavaScript fetch calls match exactly what our Flask app expects. Once we solve the mystery of the missing endpoint, we'll get our spectrograms back up and running, and everything should be as smooth as EEG gel on a brain cap. Until then, let's keep debugging and see what we uncover. And remember, folks, coding is like an EEG signal. It has its ups and downs, but we always find our rhythm in the end. Stay tuned for more. It looks like we're getting a series of 404 not found errors when trying to fetch EEG data and spectrograms from certain endpoints, specifically /fetch EEG data and /fetch spectrogram. Let's break down what's happening and where things might be going off track. What we know. 1. Successful requests. Several requests are succeeding, like those to /get related data, get sub IDs, get label, and /get spectrogram ID. This suggests that the server is properly set up to handle these endpoints and that the data being requested is accessible. 2. Failed requests. The requests to /fetch EEG data and /fetch spectrogram are consistently returning a 404 error. This means that the server cannot find the resources associated with these requests. The errors in the console also align with this, indicating file not found issues for both the EEG data and spectrograms. Diagnosing the issue. 1. 404 error for /fetch EEG data. The root /fetch EEG data is supposed to handle requests for EEG data based on the specified EEG ID and electrode. However, the error logs indicate that the server is unable to find the corresponding .parquet file. Check the data directory. Make sure the .parquet file for each EEG ID exists in the static HMS-harmful brain activity classification train EEGs directory. For example, if the request is for EEG ID equals 151799604, the server is looking for a file named 151.71904.parquet in that directory. Confirm file names. The EEG IDs must match the file names exactly. Ensure there are no discrepancies like leading trailing spaces, file extensions, or any other differences. 2. 404 error for /fetch spectrogram. The /fetch spectrogram endpoint is responsible for fetching spectrogram data, and it is looking for specific .parquet files in the trained spectrograms directory. Validate file paths. Similar to the EEG data issue, check that the spectrogram files, e.g. 646511A3.parquet, 64571371.parquet, 16C414271.parquet, are actually present in the static HMS-harmful brain activity classification /train spectrograms directory. Correct file naming. Again, confirm that the file names exactly match the spectrogram IDs being requested. Even a small typo or mismatch in names will cause the file not found error. Steps to resolve the errors. 1. Check the file system. Manually verify that all the expected .parquet files for EEG data and spectrograms exist in the correct directories. Train EEGs and train spectrograms. Ensure there are no typos, missing files, or incorrect paths. 2. Logging for debugging. Add more detailed logging to the Flask endpoints to print out exactly which files are being looked for and where. This can help pinpoint whether the server is mistakenly looking in the wrong directory or if the file names are somehow being altered. 3. Verify endpoint URLs in JavaScript. Double-check the JavaScript code to make sure the URLs being constructed in the fetch calls correctly match the endpoints defined in Flask. Make sure there are no accidental changes or dynamic issues causing incorrect requests. 4. Check Flask error logs. Look deeper into Flask's error logs. The 404 messages might provide additional hints if there are any path or configuration issues that are not immediately obvious from the code. 5. Run in debug mode. Running the Flask app in debug mode is already enabled, app.run debug true, which is great. This will continue to provide detailed output for any errors or issues encountered. Watch the terminal closely for any additional clues. Wrapping up by ensuring that all the files are correctly named and located in their respective directories, and that the paths in the code match perfectly, we should be able to resolve these 404 errors and get our EEG data and spectrograms fetching smoothly again. Keep debugging, and remember, every error is just another step toward a fully functioning app. Let's find those files and get our brainwaves back on track.
Okay, we only have a sample, we only kept a sample of the data because the original data set was too large. So there might be a list. It's probably in the CSV file. The list might be for the whole data set, but we actually need to look at only the files that are available in this sample. How do we go about that? So we're currently having the page loading okay on first page load. But then when we're trying to select a different EEG ID, we getting drop downs not yet populated message. Okay, so well, we have the page displaying the spectrograms when loading the first time, so that's great.
That's fantastic to hear. It's great to know that the spectrograms are now displaying properly on the initial page load. This means that the changes to ensure proper handling of the asynchronous dropdown population and data fetching are working as expected. Next steps. Since the initial loading works well, here are a few things to focus on next. 1. Test dropdown interactions. Now that the initial load works, test the interactions when changing the dropdowns, like EEG ID, sub ID, and electrode, to ensure that the spectrogram updates correctly every time a user makes a new selection. Watch for any errors in the console, such as missing data or fetch issues, which might indicate further tweaks are needed. 2. Refine user feedback. Consider adding user feedback elements, like loading spinners or progress bars, while waiting for data to be fetched. This will improve the user experience by visually indicating that a background process is underway. 3. Optimize data handling. If you're working with a large data set, think about optimizing data fetching, such as by implementing caching mechanisms on the client or server side to reduce the load time and improve responsiveness. 4. Enhance error handling. While the current error handling is functional, you can improve it by providing user-friendly messages in the UI. For instance, if a fetch fails due to a missing file, display a message explaining the issue and offering guidance or alternatives. 5. Fine-tune visual elements. Now that the core functionality is working, you can start refining the visual elements. Adjust color schemes, plot sizes, and other UI components to make the application visually appealing and more informative. 6. Consider additional features. Depending on your project's goals, consider adding more features. This could include functionality for users to save or export spectrograms, overlay multiple datasets, or even use different visualization techniques, like 3D plots or dynamic interactive charts. Keep iterating. Keep testing and iterating on the design and functionality. Each adjustment brings you closer to a polished application that meets your vision and offers users a seamless and insightful experience. If you run into any more issues or have any other questions, feel free to ask.
So the page is loading okay the first time, but then when selecting any of the drop downs, I'm getting the following errors. Can you comment on how well this dataset is organized? Without generating any new code. Don't mind, don't be afraid of being critical.
Absolutely. Let's dive into a critique of the dataset's organization based on the information you've provided and the structure we've been working with. Observations on the dataset organization. 1. Separation of data types. The dataset is neatly divided into two main types: train EEGs for EEG data and train spectrograms for spectrogram data, which is a good start. This separation allows for focused operations on specific types of data without confusion. However, a more descriptive naming convention or folder hierarchy could enhance clarity. For example, adding subfolders by electrode or patient could make it easier to locate specific data subsets. 2. Inconsistencies in available files and metadata. There seems to be a disconnect between the metadata, like train.csv, and the actual available files. For instance, the metadata references files that aren't present in your sample, leading to file not found errors. This suggests that the dataset might have been partially copied or truncated, which is problematic for developing a reliable data pipeline. If the dataset is a reduced version, it would be better to prune the metadata to match only the files in the sample, reducing mismatches and making the data immediately usable. 3. File naming conventions. The file naming conventions for the .parquet files appear to use numerical IDs, which are great for machine processing, but not particularly human-readable. This could make debugging and manual inspection tedious, especially when dealing with a large number of files. Adding a prefix to indicate the type of data or including a descriptive keyword might help, e.g., EEG 124.931.parquet instead of just 110.24.931.parquet. 4. Lack of comprehensive metadata. While there is a train.csv file that presumably contains essential metadata like EEG ID, sub-ID, patient ID, etc., it may lack other contextual information that could be valuable. For instance, there is no clear indication of the recording duration, sampling rate, or electrode placement in an easy-to-access format. All of these factors are crucial for anyone performing analysis on EEG data and could be included in a more detailed metadata file or JSON schema. Number 5. Handling of missing data. The dataset doesn't seem to handle missing data gracefully. There are many instances where certain data files are absent, which leads to HTTP 404 errors. This implies that either there was a lack of data cleaning and preparation before deployment, or there was insufficient checking for the presence of files. Before deployment, a pre-processing step to ensure all referenced files exist, or a mechanism to handle their absence gracefully, is essential. 6. Error-prone design choices. The dataset is currently causing errors in the client-side JavaScript due to issues like drop-downs not being properly populated with available data. This indicates that the data organization isn't aligned well with the front-end application requirements. If the dataset Based on this sample from the train.csv file, here are some additional observations about the dataset. Observations on the CSV data. 1. Clear organization of fields. The CSV file is well structured with clearly labeled columns. It includes essential fields like EEG, EEG sub-ID, spectrogram ID, patient ID, and various labels and votes, expert consensus, seizure vote, etc. This makes it easier to understand the data relationships and identify the primary keys, EEG ID and EEG sub-ID. 2. Use of IDs. The dataset uses numerical IDs, e.g., EEG ID, label ID, patient ID, for indexing, which is standard practice in data management. However, while this is efficient for processing, it is not immediately informative without accompanying context or a lookup table that explains these IDs, e.g., patient demographics or study-specific details. 3. Consistency in data entries. The entries are consistent, with each row representing a unique EEG recording segment, EEG sub-ID, and its associated spectrogram data, spectrogram ID, and spectrogram sub-ID. This is a good approach for maintaining granularity and ensuring that each piece of data is identifiable. 4. Potential for redundancy. Certain fields, such as EEG ID, patient ID, and expert consensus, repeat across multiple rows. While this is necessary for a relational dataset to maintain unique combinations of EEG ID and EEG sub-ID, it may lead to redundancy. In some cases, separating metadata into a different table could reduce repetition. For example, patient-specific information or overall EEG details could be stored separately to avoid repeating these for every subentry. 5. Absence of data description. The CSV file lacks any description or context for the fields it contains. While column names are somewhat self-explanatory, more detailed descriptions or definitions, e.g., what constitutes a seizure vote or how EEG label offset seconds is determined, would enhance clarity. Including a README or data dictionary file alongside the CSV would help users understand the nuances of the dataset. 6. Handling of missing data. From the sample provided, there is no indication of how missing data is represented. Are null values or empty strings used? Having a standardized way to handle missing data, such as using NA or a specific sentinel value, is crucial for consistency, especially when the dataset is large. 7. Lack of timestamp or duration details. There is no direct indication of the timestamp or duration of the EEG recordings, except for the EEG label offset seconds field, which indicates offset. However, more comprehensive timing details, like start and end times or recording duration, would be useful for understanding the temporal aspects of the data. For instance, the specific time window each EEG sub-ID represents is unclear without more context. 8. No obvious quality control indicators. There is no explicit mention of data quality indicators in the CSV. For example, it could be helpful to know if certain EEG recordings were flagged for quality issues, artifacts, or noise. This would be useful for downstream analysis to filter out less reliable data. 9. Potential data duplication across sub-IDs. All the sub-IDs in the example are under the same EEG ID, 162818042, which is expected, but it raises a question of whether multiple EEG recordings per patient are adequately distinguished. If different recordings or sessions have the same EEG ID but only vary in EEG sub-ID, it could be confusing unless EEG ID is strictly unique per session. 10. Opportunities for enrichment. The dataset could benefit from enriching additional fields such as patient demographics, age, gender, medical history, etc., would help understand variability. EEG context. Information about the EEG equipment, electrode placements, or other protocol details. Analysis metadata. Results from any initial automated analysis, such as spectral bands, detected anomalies, or preliminary classifications. Summary. The CSV file is generally well-structured, with a clear format and logical fields. However, there are opportunities to improve the dataset by adding more descriptive metadata, handling missing data explicitly, and reducing redundancy where possible. Addressing these areas would make the dataset more user-friendly and ensure its utility for a broader range of analyses.
We are not updating or changing the dataset. The dataset will remain as is, as it was already recorded in the past. So we are not changing that. There is more description on it somewhere. And we should be able to pull it out. We'll just add the text file. Called the dataset description. It's a text file. Yeah, the whole dataset is about 26.5 gigabytes. We only have a subset of it, so just a small portion. And below is the content for the dataset description text file.
The dataset description provides a comprehensive overview of the goal, structure, and content of the dataset you are working with. Here's a breakdown and commentary on its organization and utility. Dataset purpose. The purpose of the dataset is to detect and classify seizures and other types of harmful brain activity from EEG data. This is a challenging task due to the inherent complexity of interpreting EEG signals and the fact that even expert annotators often disagree on the correct labels. This reinforces the importance of having multiple expert opinions and consensus annotations to ensure reliable results. Dataset structure and files. 1 metadata files, train.csv and test.csv. These files provide metadata for the training and test sets, respectively. They include information about the EEG recordings, spectrograms, and the annotations provided by experts. The metadata is crucial for navigating the dataset, understanding which subsamples correspond to specific recordings, and ensuring the correct interpretation of the data. Train.csv metadata details include EEG ID, unique identifier for the EEG recording; EEG sub-ID, identifier for specific 50-second subsamples; EEG label offset seconds, offset time for each subsample within the recording; spectrogram ID, unique identifier for the entire spectrogram; spectrogram sub-ID, identifier for specific 10-minute spectrogram segments; spectrogram label offset seconds, offset time for each spectrogram subsample; label ID, identifier for the set of labels; patient ID, identifier for the patient who provided the data; expert consensus, consensus label provided by experts, which serves as a convenient reference; seizure LPD, DAPD, LRDA, GRDA, other vote, the count of votes from annotators for each brain activity type. This is valuable for understanding the variability and uncertainty in the labeling process. 2. EEG and spectrogram data. Train EEG contains EEG data for overlapping samples, with each column representing a specific electrode location and the EKG column for an electrocardiogram lead. The data was collected at a frequency of 200 samples per second. This folder is critical for extracting the actual EEG signals based on the metadata in train.csv. Train spectrograms contains spectrograms generated from the EEG data. The columns indicate frequency in hertz and the regions of the EEG electrodes, e.g. LL, RL, LP, RP. This is essential for visualizing the frequency components of the EEG data. 3. Example figures. Example figures / provides larger copies of images used in the Overview tab, likely for visual reference or educational purposes. Commentary on dataset organization. 1. Overall structure. The dataset is well organized, with clear separation between metadata, train.csv, test.csv, and actual data, train EEG / train spectrogram /. This modular structure is advantageous because it allows for flexible data handling and processing. By separating metadata from raw data, it ensures that the core information about the dataset is easily accessible without needing to parse through large data files. 2. Use of unique identifiers. The consistent use of unique identifiers, such as EEG ID, spectrogram ID, patient ID, allows for straightforward cross-referencing between metadata and data files. This makes it easier to extract relevant subsets of data for specific analyses. However, without direct context, like a mapping file, these IDs themselves might not be very meaningful, making documentation essential. 3. Clear annotation information. The dataset provides a detailed breakdown of annotation votes and expert consensus labels. This is a valuable approach because it conveys both the primary label and the degree of uncertainty or disagreement among annotators. It also provides a richer dataset for training machine learning models, allowing for the exploration of ambiguity in human annotations. 4. Limited access to full data. The description mentions that only a subset of the test data is available for download, with the rest accessible only during submission scoring. This approach is common in competitions, but means that any offline experimentation or development must be done with limited data. This might limit the ability to fully validate models locally before submission. 5. Description completeness. While the description is thorough, it lacks details on some potentially important aspects. Data quality. There is no mention of quality control measures or data pre-processing steps that were applied before sharing the dataset. Understanding how noise, artifacts, or outliers were handled would be useful for those analyzing the data. Field definitions. Some fields, e.g. label ID, expert consensus, could benefit from more detailed explanations or examples. While their general purpose is clear, specific values or ranges are not always obvious. Data size and storage. Mentioning the full size of the dataset, 26.55 gigabytes, is good, but additional guidance on how to handle and process such large files might be helpful, especially for those working in limited computing environments. 6. Opportunities for additional documentation. Given the complexity and size of the dataset, a more detailed data dictionary or documentation file could be beneficial. This could include examples of how to interpret the metadata, tips for handling the large data size, and links to further reading on EEG and seizure detection. Conclusion. Overall, the dataset appears to be well structured and suitable for its intended purpose of detecting and classifying harmful brain activity. However, additional documentation or resources could help users navigate its complexity more effectively, especially given the dataset's large size and the challenging nature of EEG data analysis. The provided subset allows for meaningful analysis, but users will need to rely heavily on the metadata to extract and interpret the relevant EEG and spectrogram data correctly. This competition provides a unique and challenging opportunity to apply machine learning and deep learning techniques to detect and classify seizures and other types of brain activity using EEG data. Let's discuss some aspects of the dataset and the competition details based on the provided information. Got it. Focusing on the dataset itself, here are my thoughts. Organization of the EEG dataset. The dataset is organized to represent the complexity of EEG data analysis, with detailed metadata and accompanying EEG and spectrogram data files. It consists of two main types of files: the train.csv file containing metadata and the EEG and spectrogram data files located in the train EEGs and train spectrograms directories, respectively. Positives. 1. Clear metadata structure. The train.csv file provides a well-organized structure for metadata. It includes essential fields like EEG ID, EEG sub-ID, spectrogram ID, spectrogram sub-EED, and several label-related columns. This structure makes it easier to match EEG data segments with their corresponding spectrograms and the labels assigned by experts. 2. Comprehensive annotations. The metadata file includes detailed annotations that capture expert consensus on various EEG patterns, including seizure, LPD, GPD, LRDA, GRDA, and other. Additionally, it provides specific votes for each pattern, which reflects the variability and uncertainty often found in EEG data interpretation. 3. Inclusion of multiple data modalities. The dataset includes both time domain EEG signals, train EEGs, and their corresponding frequency domain representations, train spectrograms. This dual modality is useful for comprehensive analysis and allows users to explore different feature extraction techniques. Negatives. 1. Incomplete data files. One of the main challenges is that not all EEG or spectrogram files are present in the reduced dataset subset. While the metadata, train.csv, might list all entries from the original dataset, only a sample of the corresponding EEG and spectrogram files is available. This could lead to errors or missing data during processing if not handled carefully. 2. Large data volume. Even though the dataset is only a sample of the original, it still involves handling relatively large volumes of data. Each EEG file represents a 50-second long recording sampled at 200 Hz, leading to high-dimensional data. This can create storage and memory challenges during data processing and model training. 3. Ambiguity in labeling. While the dataset includes a wealth of annotations, the presence of edge cases and varying levels of agreement among experts can complicate analysis. For example, there are cases where different experts have labeled the same EEG segment differently, which reflects the complexity of EEG interpretation, but also requires sophisticated approaches to handle these discrepancies. 4. Lack of pre-processing information. The dataset lacks detailed information on how the EEG and spectrogram data were pre-processed before release. Knowing the types of filtering, artifact removal, or normalization applied would help ensure that subsequent analyses are consistent and valid. Without this information, researchers might have to repeat or guess these steps, potentially leading to inconsistencies. 5. Sparse documentation for data use. Although there is some documentation provided, additional information on how to effectively use the dataset would be beneficial. For example, clear guidance on the recommended pre-processing steps, strategies for handling missing data, or suggestions for feature extraction would help users make the most of the data. Suggestions for improvement. 1. Provide sample code for data handling, including scripts or notebooks that demonstrate how to load, visualize, and pre-process the data would make it easier for users to work with the dataset effectively. This would be especially helpful for those unfamiliar with EEG data formats or who are new to working with biomedical signal data. 2. Clarify missing data handling. Since not all files from the original dataset are present in the subset, adding a mechanism to handle missing files gracefully would be essential. For example, functions to check the existence of data files before attempting to load them could help prevent runtime errors. 3. Add more contextual information in metadata. Providing more context about each EEG recording, such as the patient's clinical background, could enhance the dataset's usability for specific research questions. While this may not be possible due to privacy concerns, even anonymized or aggregated information could be valuable. 4. Document preprocessing steps. A detailed description of any preprocessing applied to the data would help ensure consistency across different analyses. This could include information about filtering, noise reduction, or normalization techniques used before releasing the dataset. 5. Improve metadata alignment with available data. Aligning the metadata in train.csv with the actual subset of data files available would prevent confusion and errors. If the metadata only lists available files or flags unavailable ones, users can quickly identify which data points are accessible. Final thoughts. The dataset is thoughtfully designed to capture the complexities of EEG interpretation, reflecting both the promise and challenges of automated EEG analysis. While it includes a rich variety of data and annotations, the organization could benefit from more detailed documentation, pre-processing information, and alignment between metadata and available data files. These enhancements would make the dataset easier to use and more effective for research and development purposes.
all this knowledge. Can we get back to coding? So essentially, if we want to scroll the data using the different column labels. Okay, so the thing is that in our current data set, we only have 100 entries for EEG and 100 entries for the spectrograms. Anyhow, when we select something from the dropdown, all the other dropdowns should get updated. We need to make sure, for example, that when we selecting a different electrode, that the specific spectrum is being loaded correctly. Loaded correctly.
Absolutely. Let's dive into the changes and updates with a narrative flair, complete with all the technical nuances wrapped up in a way that keeps it engaging. Imagine you're embarking on a journey through the mystical land of JavaScript and HTML, where dropdowns don't just sit there passively, they come alive and respond to your every command. Hasha, what's happening with the dropdowns? So, you have this amazing web application that visualizes EEG data, a powerful tool for analyzing brain activity, like spotting those pesky seizures or rhythmic delta waves. The app's main feature relies on several drop down menus that allow users to choose various parameters such as EEG IDs, electrode types, expert consensus, and spectrogram IDs. The goal is to ensure that when you pick something from one dropdown, the rest of them get the memo and update themselves accordingly. This is like saying, hey, dropdowns, don't just sit there like lazy buttons. Pay attention. To make this magic happen, I've introduced a few changes to your JavaScript. First up is the populate dropdown function. This clever little function is like the waiter at a fancy restaurant who brings you only what you want to see on the menu. It takes three ingredients: a URL to fetch data from, a dropdown element to populate, and an optional selected value. With these, it fetches data from the server, clears any previous entries, and then carefully fills the dropdown with fresh, relevant options. If there's a specific choice you want to highlight, it makes sure that option is pre-selected. Think of it like having a favorite table at your regular coffee shop. Now, the star of the show is the Update Dropdowns function. This function has the crucial job of orchestrating the dynamic behavior of all dropdowns whenever a user makes a selection. Every time you select an EEG ID, change an electrode, or make a choice in any of the dropdowns, this function springs into action like a conductor leading an orchestra. It fetches the appropriate data for all related dropdowns based on the current selections. This means it checks, okay, what EEG ID did you pick? What electrode type did you go for? And based on those choices, what should the spectrogram sub-ID and label offset be? It then updates all the drop-down menus so that each one reflects only the relevant and available data. This process ensures that the user always has access to valid options that match the current dataset context. No more picking a non-existent sub-ID and getting an awkward blank stare from your app. To ensure the dropdowns stay in sync with each other, I've added event listeners to each dropdown element. These listeners act like vigilant guardians, always on the lookout for changes. The moment a user dares to change a selection, they trigger the Update Dropdowns function. This keeps everything smooth and interactive. For example, if a user selects a different EEG ID, the sub-ID dropdown immediately updates to show only the sub-IDs that are available for that specific EEG ID. No more confusion, no more missteps, just seamless data exploration. Finally, the script initializes everything when the page first loads. This means the Update Dropdowns function is called as soon as the page is ready, populating all the dropdowns with their initial data. It's like setting the stage before the first act of a play. Everything is in place, and the show can go on without a hitch. Why does this matter? These changes make your web application much more user-friendly and intuitive. Users won't have to worry about selecting invalid combinations or wondering why their spectrograms aren't updating correctly. The application now feels much smarter as it responds to each The updated screenshot shows that the application is still encountering the EEG ID is missing or invalid and spectrogram ID is missing or invalid errors. However, the logs indicate that the dropdowns for expert consensus, electrode, and patient ID are successfully populated with data. Analysis of the current situation. 1. EEG ID dropdown issue. The error EEG ID is missing or invalid suggests that the EEG ID dropdown is not properly populated with data, or Based on the screenshot you provided and the current state of the code, it appears that several of the requests to the Flask backend endpoints are resulting in 404 not found errors. Let's go through the steps to identify the main issues and provide solutions to fix them. Issues observed. 1. 404 errors. The JavaScript is trying to call several backend endpoints that are either incorrectly defined or the requests are not matching the expected paths on the server. Sure. Let's dive into how the JavaScript code was completely revamped, making it more dynamic, efficient, and fun to interact with. First off, we started by focusing on the big picture, creating a seamless and interactive experience for users exploring EEG data through the Seizure Fuzz application. The new code is like a well-orchestrated symphony, where each function plays its part in perfect harmony with the others. The aim was to keep things flowing smoothly, reducing lag and minimizing errors, so users have the best possible experience. How did we improve the code? We took the original code, which had a lot of good ideas but needed some polishing, and made it more robust by focusing on several key aspects. 1. Improved data fetching and drop-down handling. The first thing we did was improve how the dropdowns, like EEG IDs, electrode choices, and spectrogram options, get populated. The new code uses asynchronous functions, async await, to make API calls to the server, ensuring that data is fetched efficiently. These functions are like messengers, quickly fetching information from the server and ensuring the dropdown menus are always filled with the most current data. If something goes wrong during this process, such as the server returning an error, our code catches these issues gracefully and logs a friendly message in the console. This means no more mysterious failures or blank dropdowns, just clean, well-handled errors that make debugging easier. 2. Smarter event handling. Next, we added smart event listeners that spring into action whenever a user makes a change, like selecting a new EEG ID or switching electrodes. These listeners trigger updates to other dropdowns and charts, ensuring all the information stays in sync without manual intervention. The key here is responsiveness. The application dynamically adjusts based on user input, making the data exploration feel smooth and intuitive. NAR 3. Dynamic chart and spectrogram updates. We then revamped how the charts and spectrograms are updated. The code now makes real-time calls to the server to fetch EEG data and displays it using Plotly, a powerful visualization library that can handle complex datasets like a pro. By plotting data dynamically, users get instant visual feedback as they navigate through different EEG signals or spectrogram views. This turns a static experience into an interactive playground for data analysis. 4. Enhanced error handling and user feedback. The new code is designed to be much more user-friendly. We've added more comprehensive error handling throughout the script to ensure users aren't left in the dark if something goes wrong. Instead of simply failing, the code logs clear messages in the console that explain what went wrong and why. This helps developers quickly pinpoint any issues and makes troubleshooting a breeze. 5. Modular and maintainable structure. We also organize the code into neat, modular functions. Each function is focused on a single task, like fetching data or updating a chart, making the code easier to read, understand, and modify. This means future developers, or even our own forgetful selves, can jump in and make changes without getting lost in a spaghetti mess of code. NAR 6. Dynamic environment awareness. Lastly, we added a little intelligence to the code by letting it know where it's running. A clever function checks if the application is on the production server or a local development machine. Depending on this, it adjusts its behavior accordingly, ensuring that everything runs smoothly no matter where it's deployed. Why these changes matter. These updates are like giving your application a turbo boost. By making it more responsive, smarter, and easier to maintain, we ensure that both the users and developers have a better experience. Users can now enjoy seamless interactions with the data without annoying lags or cryptic errors. Meanwhile, the developers can sleep easier, knowing the code is robust, well organized, and ready for anything the future might throw at it. So, what does this all mean? It means the Seizure Fuzz application has leveled up. It's not just another data viewer. It's now a sophisticated, user-friendly tool that's ready to handle complex EEG data with ease. And that's something Absolutely. Let's wrap up today's session. Today, we worked on building and debugging a dynamic EEG data viewer using Flask and JavaScript. While we faced a few hurdles in getting all the data to display correctly, we covered a lot of ground on troubleshooting techniques, back-end route handling, and front-end data fetching. Remember, debugging is an essential part of the development journey, and every challenge brings us closer to a more robust and polished application. Keep testing, refining, and experimenting. Thanks to everyone who joined the stream today. We appreciate your patience and participation. Stay tuned for more updates, and we'll see you next time. Bye for now, and keep coding. Take care. Absolutely. Before we sign off, I want to invite all of you to check out BioniChaos.com. It's the place where you can explore more of the exciting projects we're working on, including tools for visualizing and analyzing biomedical data like EEGs and ECGs. Your feedback and support are always welcome, and there's so much more to come. Thanks for tuning in today, and we look forward to seeing you at BioniChaos.com.